Well, thank you very much for this kind invitation to come to Voronezh and talk with you about my research. It's the first time I've ever been in Russia and the first time I've ever been in Voronezh, so thank you very much for inviting me. My topic today is the origin of life on Earth and elsewhere with a question mark. And so what I'll discuss with you today is how we think life on our planet started and whether those processes could happen elsewhere. And if so, where might we look for that? Let's just start out by defining life as we know it. Okay, remember, I'm not going to discuss any kind of far out stuff that like we don't know it, because since we don't know it, we wouldn't know anything about it. So we're going to start with life as we know it. And there are two fundamental requirements for life as we know it: liquid water and carbon-based polymers. Citrus nucleic acids, which are the compounds like DNA that carry genetic information, and proteins, which are made up of amino acids, and some proteins act as catalysts for reactions. These are called enzymes. So water is important because it's an ideal solvent. Everything is soluble to some degree in water. Now, why is being soluble important? Let's say we have compound A here and compound B here. They would not know each other existed, just sitting there like that. Water dissolves them, and as a result, they can interact. And that's a key. Water allows compounds, elements to interact, and thus you can have chemistry taking place. Polymers are needed to carry out the central biological functions of replication, making copies of ourselves, and catalysis, to make reactions that otherwise would be very, very slow to go very fast. And without these two vital components, life as we know it is impossible. Now, one thing to remember about this, and this is an important issue that I find frustrating a lot, is finding water somewhere on another planet does not prove that life exists there. It only says that the potential for life is possible. But just water by itself is not life. It just says that the chemistry that leads to life or supports life is possible. Okay, the first person to offer a real science explanation of how life may have started on Earth was Charles Darwin. Before this, people had all kinds of weird hypotheses about how life began. One famous example of life was so-called spontaneous generation. You took a piece of meat and put it on the table and left it there for weeks, and pretty soon flies and maggots would be in the meat. And that was the origin of life. And that's pretty obviously unscientific because we know flies already existed. And so Darwin wrote a letter to his friend, Hooker, and he said, but if, and oh, what a big if, we could conceive of some little warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, are present, that a protein compound is chemically formed. And so here's the first idea that natural processes interacting in an environment produce compounds that were essential for further chemistry that leads to life. One of the first people that really put this in a very rigorous scientific theory was one of your countrymen, Alexander Oparin. And he offered the first real science-based explanation for the origin of life in this little paper that he published in 1924. And unfortunately, that paper was not known in the West at all. But Oparin then published a bigger version of this hypothesis, again in Russian in 1936, and then again in English in 1938. And at that point, it was widely available to other scientists who could study this idea and evaluate how it might be tested. I had the good fortune of meeting Oparin, who came to La Jolla, University of California, San Diego in 1968. And I'd gotten a copy of his book, so I asked him to sign it. So I feel very privileged to have a signed copy of his book. Now, what Oparin said was that life on Earth formed through a series of reactions that first made simple compounds that gradually became more complex. In other words, you start making simple compounds like amino acids. They reacted with each other and formed more complex molecules until eventually you had some complex molecule that could replicate. Now, remember, our definition of life is very simple. It has to undergo replication. It doesn't mean it's a cell. It can mean a molecule that can make a copy of itself. It has to store information, so it has to be a pretty complex molecule. This idea gave rise to what's called the primordial soup. And this was first noted by an English biologist, John Haldane, in 1929. So he didn't know Oparin's idea, but he suggested independently that there was this warm, dilute soup or prebiotic soup on the Earth that contained all these simple compounds that reacted to form more complex molecules. So, what is the minimum requirement for life in this case? We assume that life is carbon-based. And I can discuss this with you if you're interested why I feel that's the case. In the most simple forms, this entity, and remember I'm calling it an entity, not a living or a cell or something that you can see under a microscope necessarily. It could make copies of itself, although the replication was not exact. So mutants could form that would have some sort of advantage, and they would then multiply more and become the dominant molecule in the system. And then, in a sense, this is the beginning of evolution. You go from simple things, you get some mutation that changes it, that becomes the most successful thing, and this evolves into more and more complex things. Now, why is this imperfect replication so important? Because that means there will be changes in the system that occur over time. And if you don't have those changes, nothing will happen. Let me give you the example of quartz crystals. Quartz crystals could grow and make a copy exactly of itself. But the quartz crystals on the Earth today are exactly the same as the quartz crystals were 4 billion years ago. They've not changed because they're perfect copies. So the next thing is that this entity could make what we call activated molecules, molecules that have the enhanced ability to react. So they could react more readily than the compound that was not activated. Or it may be that mineral surfaces played an important role in capturing molecules and bringing them in close proximity so they could react to form something more complex. And most importantly, this entity must live long enough, it must exist long enough to get replicated. If a molecule lives such a short time that it's never copied, the whole thing will stop, it'll die. So, today the version of the primordial soup can be summarized as follows. You have simple organic compounds that are made on the early Earth by various processes, and you see that there. Campbell's soup is a type of soup that you can buy in a supermarket in the United States, and we just took the label and changed it and made it primordial soup. I have a can of this in my office. And those simple molecules reacted and formed something more complex, which we call the pre-RNA world. RNA, remember, is ribonucleic acid, which is a very important part of our biochemistry today. But this is before RNA ever formed. This then evolved into the RNA world. This was the first truly living system on the Earth. Life consisted nothing more than self-replicating RNA molecules. I know it's hard to think of, but this was something that occurred very early in the history of life on Earth. That then evolved into the protein DNA world, which is modern biochemistry. And from modern biochemistry, you see there the tree of life with all the domains of life. And so the DNA protein world is the biology we have today. But all this other stuff preceded this. As far as the origin of life probably occurred somewhere in this pre-RNA world. And we're still trying to figure out exactly how that took place. Oh, one last thing. I want to emphasize here. You can see that circle at the end there. It is unlikely that life elsewhere would produce the same kind of tree of life, just because all of this is by chance. So let's keep that in mind as well. So how do you make organic compounds on a young planet like the Earth? And this was first tested experimentally by this young graduate student named Stanley Miller in 1953. And he was a graduate student at the University of Chicago, where a very famous American chemist was working, Harold Urey. And Urey had suggested that you might make organic compounds if you took a gas mixture different from the atmosphere today and applied some sort of energy to it. And so Miller decided to test this, and he built this apparatus, a world of glass. Now you look at this, and this looks like it's just a bunch of flasks and tubing hooked together. But it's not. It's a carefully thought out series of vessels here. The water flask there is filled with water. So that represents the ocean. The big flask is filled with gas, and that represents the atmosphere. So this is a model of the ocean-atmosphere interaction. Energy, they applied a spark discharge, lightning. And the nice thing about this is that there's a condenser there, so stuff that forms in the atmosphere would collect and run back into the ocean. So you have a system very much like rain falling, water evaporating off the ocean, interacting with the atmosphere, condensing out of the atmosphere, and running back into the ocean in the form of a river. So they chose lightning simply because lightning is a global, pretty much a global phenomenon. This is a time-lapse movie of the lightning on the Earth over a period of a few weeks in April of 1998. And you can see there's lightning everywhere pretty much, although it tends to be confined near the equator. You can see there's not much lightning in Russia during this period. A lot of lightning in the middle of the United States. So lightning is a global process. So what they did is they filled this apparatus with these gases, hydrogen, methane, and ammonia, applied this electric spark, and look what happens. Over a series of 7 days, this thing turns brown, is covered with goo. The ocean becomes dark brown as well. And so there's a lot of chemistry taking place here. So the question is, what is that chemistry? So the next thing they did is they took a sample of the water and analyzed it. And what do you know? You made amino acids, the building blocks of proteins. One of the most fundamental molecules in biology. So this simple experiment showed how you can take gases in the atmosphere and convert them to organic compounds that are part of living organisms. So this was a real breakthrough. There were other versions of this apparatus that were tested as well. And here you see one where the atmosphere flask is connected to the water flask. And what you notice here is that as the water evaporates off the ocean, it generates this big geyser of steam that's being in the spark, in the lightning. So this, in my opinion, when I saw this and I replicated this, was very much like a volcano that we see today. This is a volcano that exploded in Iceland just a couple of years ago. And what you see with all volcanic eruptions today, there's intense lightning that surrounds them. On the early Earth, there would have been gases coming out of the interior of the Earth and immediately subjected to intense lightning, and compounds could have been readily produced in this kind of environment. And so one of the models that we assume is that in the water, you had this chemistry taking place to generate amino acids. And this is really simple chemistry. I don't want to bore you with this, other than for you to remember that this was first demonstrated in 1850 by a German chemist named Strecker. And so we knew about this chemistry for a long time. We just never realized it could have happened naturally on the young Earth. So this is our model of how you may have made simple compounds and where they may have reacted to form more complex compounds. So here you have a volcano, lightning around the volcano. You're making simple organic compounds that run into this warm little pond. And in this warm little pond, there's all kinds of other compounds that start to react to start producing more complex molecules. And eventually, out of that mixture of compounds, you had something that could carry out its own catalytic self-replication. We know that gases such as methane and ammonia are widespread throughout the universe. This is a cartoon drawing of a young solar system forming somewhere. And so here you see the sun, and around it is all these dust particles. And in this gaseous mixture around this young sun are methane and ammonia. And there's also things like hydrogen cyanide and aldehydes and ketones, which are used to make amino acids. So this chemistry is probably taking place everywhere you're seeing things like this in the universe. So this is truly universal chemistry. So it's very, very likely that the kind of chemistry that Miller carried out in this simple experiment is occurring everywhere throughout the universe. We know it happened other places in our solar system because we have meteorites. Meteorites that came from elsewhere in the solar system, probably from the asteroid belt. And we look at these meteorites and we see they contain over 75 different types of amino acids. In biology today, there's only 20. These meteorites contain a bigger variety of amino acids than biology uses today. So there was an abundant mixture of amino acids that could have been present. So all of these compounds and reagents, everything were available throughout the solar system. Water was present, and you made compounds, even in the object where this meteorite came from. So it's almost for certain that this is a good model for the early Earth. So here's the model again. Early prebiotic compounds, the prebiotic soup, reacting to form complex molecules. In the pre-RNA world, the origin of life is there somewhere. This evolved into the RNA world, one of the first complex living systems, then to the DNA protein world.
This animation shows a mechanism by which RNA is replicated in a non-enzymatic manner. Single nucleotides find their complementary base on the template strand and undergo a chemical reaction to form a polymer. This reaction is possible because the nucleotides have been chemically activated so as to increase their reactivity.
So this is a cartoon showing you how life would look like in the RNA world. A lot of you aren't just thinking of life as a molecule like this, but this is a living system, and we can duplicate this in the lab. This is a cartoon of that, and we have duplicated this very chemistry in the laboratory. So we've made the RNA world. We have not yet figured out what the pre-RNA world was. That's a very intense area of research right now. But this is a timeline for the early Earth. This is the age of the Earth, starting at 4.5 billion years. And so this is the first billion years of the history of the Earth. So very early oceans form, very early simple organic compounds form. This then became more complex and led to the pre-RNA world where you had the origin of life. This evolved into the RNA world and then into the DNA protein world in less than a billion years. And so all of this took place when the Earth was a very young planet. And then once life began, it began to become more and more complex, and eventually, after for some billion years, ended up producing creatures like us. Now, let's use this model to try and predict where life might occur elsewhere in our solar system. Now you look at our solar system, you see the inner planets, which are called the rocky planets. They're Mercury, Venus, Earth, and Mars. Mercury is a small little moon-sized object. It's completely rock, it's totally dry. It's been fried throughout its history because it's so close to the sun. Venus today is a hot planet that has a very dense atmosphere of carbon dioxide. The surface temperature on Venus is warm enough to melt lead. No organism that we know could survive there. But Venus has not always been that way. Early in its history, Venus would look like the Earth. We could have had the origin of life on Venus, but unfortunately it's been obliterated as the planet became more and more hostile to organic compounds. The Earth, we know the story of Earth. We're here, and we're trying to understand how we got here. Mars, well, maybe this could have happened on Mars. We could have had the prebiotic epoch, organic compounds. We could have had these compounds becoming more complex, and maybe the origin of life, but we don't know what that would evolve into. So if you're going to look for life on Mars, you don't want to look for us by any means. And you don't want to look for organisms like bacteria. They are a real long shot. So there's been a lot of emphasis on Mars, but we don't want to forget the outer planets, the gaseous planets. They're not rocky, but we'll revisit those planets in a little bit. Okay, here's Mars today. And you look at it and you go, wow, what a terrible place to live. It's dry, it's incredibly cold at night. You think winters are cold in Moscow? Temperatures are colder on Mars all the time. And more importantly, it's being constantly baked by intense solar radiation. Well, this does not look like a very good place to live. Nevertheless, we have been optimistic that maybe some kind of living system could have evolved and survived there. When the first spacecraft landed on Mars in 1976, the first thing they did was turn on the cameras and sat there and watched to see if anything moved. If you saw something move, it was probably something alive. They didn't see anything move. And so far, when we've looked at this dirt, it's been very difficult to analyze because Mars is 35 million miles away. And so we have to be very careful as we try and do experiments analyzing organic compounds directly on Mars. We do know, though, that when Mars was a young planet, it was much different than today. It had water on it, and we think it had a lot of water. It could have had oceans. As you see here, oceans that covered a pretty large part of the Martian surface. So maybe some of this chemistry could have indeed taken place, producing some sort of living system that we could try and search for, and maybe it's adapted to the harsh environment and survived there. So this is the launch of the latest spacecraft to go to Mars. This is launched November 26, 2011. This is the Mars Science Laboratory. I happened to be there to watch this. And what was amazing to me, seeing this launch, was this rocket ignited and went out of sight in 30 seconds. You know, I'm used to seeing rockets launch and they're sort of slow getting off the surface and they're slow to fly up. This thing just went pow, off it went. And so it finally got to Mars about 8 months later, and this large rover, Curiosity, landed on the surface, and it's been there over a year now. It's been exploring, driving around, looking at the dirt and trying to search for a variety of things using a very sophisticated instrument package, abbreviated SAM, sample analysis at Mars, and it has all kinds of instruments in it. You notice there's one there called a TLS, that's a tunable laser spectrometer, and that can look at the atmosphere. One of the things that was looked for immediately was whether there was methane in the Mars atmosphere. There's methane in the Earth's atmosphere, which is produced biologically. So the presence of methane in the atmosphere of Mars might indicate some sort of biology. No methane has been found, even after many different analyses. The other instrument there is called a GC, gas chromatograph. That has the ability to look directly for organic compounds, not amino acids, but simple organic compounds. So far, it has detected organic compounds, simple things like chloromethane, which is a methane with a chlorine atom stuck on it. So we know the instrument worked. The bad news is this is stuff from the Earth. We brought this with us and the instrument's picking it up. We see no evidence of any organic compounds on Mars. So right now, all we can say is we're trying, but so far we have not succeeded in detecting any kind of organic molecules on the surface of Mars. That doesn't mean that maybe they don't exist below the surface. We have no way of drilling into the surface at the present time. So this will be something that continues. Eventually, humans will go there, and once humans get on the planet, we will forget it. We'll never know whether life started on Mars because humans will contaminate the planet. So let's hope we know the answer to whether there's life on Mars before mankind sets foot there. Now, one of the problems with doing these analyses is contamination, as you saw. And And if you detect something, let's say we detected amino acids, how do we know they're not contamination from the earth? Well, fortunately, amino acids have a very nice property that enable us to separate that out. Amino acids come in two forms, called the left and right-handed form. And if you look at them, they're mirror images of one another. If I had a mirror here, the image that would be in that mirror, and I looked over here, would be my other hand. Amino acids, because of the geometry of the atoms that make up amino acids, have left and right-handed forms. On Earth, biology only uses left-handed. When we make amino acids, like in the Miller experiment, or we look for amino acids in meteorites, they're both in equal amounts. So we assume that somehow, by chance, life selected only left-handed amino acids to make its proteins. And there's very good reasons why that had to happen. It could have been right-handed, but by chance we have left-handed. Elsewhere, it could be either. If we found right-handed amino acids on Mars, that would be absolute proof of Martian life, because we'd never see that anywhere on the Earth. If we saw left-handed amino acids, maybe we're related. Maybe we had some piece of meteorite ejected from the Earth early in its history. It landed on Mars, and life colonized the planet. And so if there's any life there and it's left-handed, maybe it came from Earth. Or vice versa, maybe we're Martians. Maybe life started there, and a meteorite fell on the Earth from Mars and seeded the Earth with life. We hope to find out if we can detect amino acids in the future. This is an instrument that's being planned for a future mission. It looks very complex, but it's not. It just takes a piece of dirt, extracts amino acids, separates the amino acids, and looks for whether they're left or right-handed or both. And this instrument you can hold in your hand. It weighs about 2 kilos and is about this big. So it's easily compatible with a rover like you see up there now. So hopefully something like this will fly in the not too distant future. And maybe we'll start to understand Mars and the potential for life once and for all. Now, there are other bodies in the outer solar system that are also interesting. Here you see Jupiter. Jupiter has 13 moons. One of these moons really stands out. If you look at it, it's whitish, and it has all these dark brown streaks on it. Where have you seen those dark brown streaks before? In the Miller experiment. So, what is white there? Ice, water ice. And by having spacecraft, the Galileo spacecraft, orbited Jupiter and flew close to Europa, and we saw the fact that there was water ice on there, probably covering an ocean that's 100 kilometers deep. This is a moon the size of our moon, but instead of the surface of the moon being covered by rocks, it's covered by water, 100 kilometers deep. That means that ocean is as big as our ocean. So maybe there's chemistry taking place there that has led to life. How do we find out? Well, we have to send a spacecraft there, and we have to be able to drill through 10 kilometers of ice to reach the ocean. Right now, we have no idea how to do that. And we have no money to do that. The idea would be that maybe in this ocean, some of these steps took place and finally gave rise to some sort of simple self-replicating entity. To get there, And suppose we can land on the surface and we have a powerful drill that we can drill through, and we have a little submarine that can go around and explore and look for molecules or look for something swimming around or whatever. Maybe in your lifetime, you will see something like this. I don't know. It depends on how much we cooperate in doing something like this, because it's a very challenging, difficult thing, and it would undoubtedly require a world effort, more or less, to do it. But maybe we'd find something. And that's our next biggest hope, is beyond Mars. Now, one thing we do know, which is really interesting, is our sun gets older. It's going to expand. You get bigger and bigger and bigger. It's going to envelop the Earth. The Earth will be no more. In 5 billion years, no Earth. But the outer solar system is going to get a lot warmer. And so Europa, which is now covered by ice, is going to thaw. And all of a sudden, you have another world where maybe everything's just right, that you could have a second generation of life, if there's not life there already. Now, at that point, humans had either figured out how to get off the planet and get out of the way, or annihilated themselves and wouldn't care whether the Earth was destroyed in one way or the other. Now, the story gets even more challenging because today astronomers have found numerous planets around other suns, other stars. Some of these have planetary systems very much like our solar system. There's Earth-like planets in these solar systems. They appear to have a density similar to the Earth. And they're just the right distance from their sun, their star, that liquid water could exist. But there are a lot of potential worlds out there where you could have this chemistry that has generated life. And this was a quote that was made by Miller and Urey in 1958. They say, "Surely one of the most marvelous feats of 20th century science would be firm proof that life exists on another planet. It would show that all our thinking about the origin of life and its evolution of that chemistry is correct." This was written in 1959. We're still not there. We don't know. We have not found proof of life on another planet. And I'll just finish with this wonderful quote from Alexander Opara. He said, "We certainly cannot say how life originated and developed on other celestial bodies under the conditions peculiar to them, but it stands to reason that organisms forming in the process of biological evolution must differ essentially from terrestrial plants and animals, since it's the environment that forms life." What he's saying is that life will evolve depending on the environment of the planet. How could that affect evolution? Well, let's just take gravity. Let's say there's a world out there that's just like Earth, but it's much bigger. The gravity would be much stronger. Organisms like us could not stand upright. We could not have a skeleton that would support us. Any kind of life would be slithering on the ground like a snake. Or it would exist in the ocean where buoyancy makes no problem for gravity. So simple things like that can change how evolution would proceed. So in closing, I love this cartoon. Do you suppose that out there somewhere, there are other goldfish in other bowls? And I would tell you the answer is no. Thank you very much. If you have any questions, don't be shy, okay? I don't understand Russian, but we have very capable people that can translate. Please go to a microphone. Okay.
Sorry, I have a question. What is the problem to dig under the surface of the Mars? There is no ice like on Saturn.
You have to let him get the microphone.
Technique cannot do it.
What's that? No, she spoke in English, but I couldn't hear her. Could you come to a microphone?
Oh, I have a little question. What is the problem to dig the Mars surface? There is no such a lot of ice like on Saturn, where a technique can dig the Mars and look what is in
Underneath. Well, we'd love to do that. Number one, we don't know how to do it. Consider the fact that you have a spacecraft that lands, okay? And you have to drill. Okay, have you ever drilled into a piece of wood and all of a sudden the wood gets really hard and the drill twists? Okay, this is drilling into the subsurface, it gets really hard and the spacecraft starts turning. So you have to anchor yourself somehow. It's very, very difficult. Then after you drill, you have to bring the sample up and give it to the instrument that can analyze it. All of that is incredibly complicated, but it's a very good question. And she's very correct in that we know a lot about the surface of Mars. We don't know anything about the subsurface.
What do you think about non-water-based forms of life, which we contain from water? And what do you think about forms of life that almost contain other liquids?
Other liquids. Why would water be so important for life? Well, let's look at water for a second. It freezes at 0, boils at 100 degrees. It's the definition of the Celsius temperature scale. 100-degree liquid range. Let's look at ammonia. Liquid ammonia has a 20-degree change between the frozen and the gas where it boils. So small temperature changes can affect whether ammonia is a solid or a gas. On Earth, you have to change the whole surface of the planet by more than 100 degrees to either boil it or freeze it. So there's a big temperature gradient. Solvent properties. Nothing can match water as a solvent. Nothing. Ammonia, methyl alcohol, everything is soluble to some degree in the ocean, including gold. If some of the people in this room want to get rich and be the latest new entrepreneur, figure out how we mine gold from the ocean. And right now it's estimated that there's over $100 trillion worth of gold in the ocean. So you could be a very rich person, but you have to get that out of the entire ocean. So maybe somebody could come up with an ingenious plan to do that. So as far as water is concerned, it's the only known solvent, and we've looked at everything that's chemically possible that has the right properties. Temperature, long temperature. Oh, another thing, which you don't even think about with water, is ice floats. Right? You make a drink and you put ice and it floats to the surface. That's totally unique. If you made ammonia ice, it would sink. Now, why is that important on the Earth? Well, let's say you have an ocean where the ice is denser and sinks to the bottom. It can never see any sunlight, it never see any energy, it'll never melt. The whole ocean would fill up with ice. So, something simple like ice floats is also important.
Thank you.
Any questions? Okay, thank you very much.
Друзья, минуточку внимания. Всем слышно без микрофона? У нас небольшое объявление есть. Значит, сейчас следующая лекция начнется в 5 часов. Вот, сейчас такой перерыв на обед. Вот, и когда будете выходить из зала, пожалуйста, сдайте вот наушники. А затем те, кто планирует посетить вторую лекцию, придите, пожалуйста, чуть-чуть пораньше, где-то в половине пятого, чтобы, вот, скажем так, не создавать очередь и организованно снова получить наушники и уже прослушать вторую лекцию. Спасибо. Давайте поприветствуем.